Hi, welcome to UpTop Solar. My name is Gwendoline Espy, and I will be walking you through the Solar 101 series. In this video, we will be going over choosing a PV module. The assumption here is that you have already chosen an inverter or solar charger. And if you haven't, that's okay. I just suggest watching my previous video. In this video, we will learn some solar module terminology and the main types of modules. Then we'll review some inverter specifications that are important before selecting a module. Then lastly, we'll go over module specifications to determine if it will work with the inverter specifications. Are you following still? If not, that's okay. That's why we're here. We're here to learn. So let's solar. A PV module is an assembly of photovoltaic cells mounted in a framework for installation. A photovoltaic cell is a semiconductor device that uses sunlight as a source of energy and generates direct current electricity. PV modules consist of PV cell circuits sealed in an environmentally protective laminate and are the fundamental building blocks of PV systems. A collection of PV modules is called a PV panel, and a system of panels is an array. This is the final result, is an array. An array is the total PV system, and it can be as small as 2 modules to as large as thousands of modules. I wanted to touch base on this because oftentimes we'll interchangeably use solar panel and solar module when what we mean is a module. So some people might say, I don't know what solar panel to buy, but really you should be saying, I don't know what solar module to buy, unless you're actually buying a panel. But I guess it doesn't matter. It's just semantics. But I just wanted to share that with you. Let's review the three different types of solar modules. The first one is monocrystalline. It is the most efficient and it's the priciest. If space is a constraint, you probably need a higher efficiency module in order to maximize harvest for the space available. These tend to have a darker black color if appearance is important. Next is polycrystalline. It's a lower cost option, but it's also lower performance. These tend to have a bluer color if that's important to you. Lastly is thin film. This is flexible, which can fit into a variety of surface shapes if that's an issue. It is, however, the lowest performance. Once you have chosen an inverter, you will need to identify the important specifications that will affect the decision on which PV module you'll get and how many modules you will need. This is an example of SMA Sunny Boy 3.0 US model. This is a grid tie inverter. We're going to focus on the input, or the DC specifications, as that will influence our PV selection. First is connected PV power. This will limit the number of modules you can connect to the inverter. Next is the maximum voltage. If you were to connect more than this, then you may damage the inverter, and this is often not under warranty. The inverter will need a minimum voltage to power up and operate. I like to use the lowest MPPT voltage to determine this. Sometimes they have a minimum operating voltage that is lower, but then you're not using the inverter's MPPT. Any lower, the inverter might not power up or not be used efficiently. Now that I'm looking at this, I would have actually used that start voltage of 125 volts. Normally, these DC voltage or start voltage are below that lower MPPT range. So usually they're below that 100 volts that I have highlighted. But now that I'm looking at it, it's above it. So I would have used actually that 125 volts. Last is the max short circuit current. Again, connecting more than this could lead to damage, and that's often not under warranty. Let's talk about modules in series and strings. Strings can also be called modules in parallel. Wiring modules in series is connecting along a single electrical path, and each module has the same current running through it. The voltage across the circuit is equal to the sum of the voltages across each module. Connecting in series creates one string and adds up the voltage and power. The current running through the string remains the same. Here we have a module with an open circuit voltage of 13 volts and 60 watts each. A string of 6 modules will result in 78 volts and 360 watts, but the current remains 6.3 amps in that string. Here, as we connect these modules in series, the voltage increases, the power increases, but the current running through it remains the same. Strings connected in parallel are connecting along multiple paths, and each string should have the same voltage across it. The current through the connection, or the current to the junction, is equal to the sum of the currents through each string. It's like two highways, all right? So if we had two highways that are representing two strings, and both highways are the same length. So length is representing, in this analogy, voltage. So they're the same length, right? But when they combine at one point at an intersection, which is that parallel connection, the traffic combines, or the current in this case. The voltage doesn't change, the length of the highways don't change, but the amount of current, or the amount of traffic, increases by double, assuming that they have the same traffic in each one. So that's how that works. So two strings will add the current of each string and power. Adding up both strings will end up with an array of 78 volts, 720 watts, and a short circuit current of 12.6 amps. Here are the important specifications that we need to look at in order to pick the right module. Power is the power per module. Each module will add up to the total power. You need to make sure that you don't connect more than the inverter max power. Open circuit voltage is the maximum voltage that the module can output. As temperature decreases, this causes the open circuit voltage to rise. So in order to make sure you don't connect too much voltage to the inverter, you need to consider the lowest temperature and calculate this using the temperature open circuit coefficient, voltage coefficient. Using this coefficient, you can calculate the temperature adjustment and thus the max voltage. Each module connected in series in a string increases the open circuit voltage. The VMP, or sometimes it's called the VPM, or I've seen it also the VMPP. Confusing, right? It's lower than the VOC. And this is the operating voltage. Because voltage fluctuates with temperature, you need to calculate what the lowest voltage may be to ensure that it's within the inverter's minimum MPPT voltage for best performance, in my opinion. You could also compare this to the lowest operating voltage, but I like to use the low end of the MPPT voltage. Use the P max temperature coefficient to calculate this. If this is not provided, then you can use the open circuit voltage temperature coefficient. Each module connected in series in a string increases that VMP. Lastly is the short circuit current. The maximum short circuit current connected to the inverter should not be exceeded. Each string increases the short circuit current for the array. I'll just touch on this topic. This is the equation to calculating the maximum voltage at the lowest temp using percent per Celsius temperature coefficient. One thing to note is when you are using a percent per Celsius or percent per Kelvin, the spec will give you something like at the bottom, negative 0.24% per Celsius. When you actually do the calculation, you have to take it out of the percent, meaning that it is going to be 0.0024 when you actually do the calculation. Now let's take a look at an actual PV specification together. This is Silfab, a US module manufacturer. We have two columns here, one labeled STC, which stands for Standard Test Conditions, and another one called NOCT, which is Nominal Operating Cell Temperature. Standard test conditions is an industry-wide standard to indicate the performance of PV modules and specifies a cell temperature of 25 degrees Celsius and a radiance of 1,000 watts per meter squared. This is a major solar panel output performance testing condition used by most manufacturers and test bodies. Now let's talk about nominal operating cell temperature. A PV module will typically be rated under standard test conditions. However, when they are operating in the field, they typically operate at a higher temperature and at a somewhat lower insolation conditions. In order to determine the power output of the solar cells, it is important to determine the expected operating temperature of the PV module. NOCT is defined as temperature reached by an open-circuited cells in a module under different conditions. These conditions differ from standard test conditions, like irradiance is not 1,000 watts per meter squared, but 800 watts per meter squared. And instead of 25 degrees Celsius air temperature, it's 20. Most manufacturers will have the STC specifications. Anything I'm saying can also apply to the NOCT conditions. From earlier, our first specification we looked at was power. Here we have module power, Pmax. For this model, it is 360 watts. The next spec that we talked about was open circuit voltage. And that's here. For this model, it is 44.5 volts open circuit. This will most likely have to be adjusted using a temperature coefficient. This is the voltage at 25 degrees Celsius. Here we have our temperature coefficient, VOC, and it is negative 0.28% per Celsius. Every degree that you are below 25 degrees Celsius, the voltage increases by 0.28%. That's what this means. Next is the maximum power voltage, or it looks like it's labeled here as VP max. Now that we checked for the lowest temperature, highest voltage condition, we also need to check the highest temperature, lowest voltage condition. And this is the voltage that we use to make that calculation. So we do the exact same calculation, but now with high temp, and we will use the temperature coefficient Pmax to do that as well. Last is short circuit current. So we have a short circuit current of 10.5. There is a temperature coefficient for this. Typically I haven't seen many people do this calculation just because the effects are so small. This is 0.064 of a percent per Celsius. Generally, you definitely do the VOC. Most people do also the minimum voltage using Pmax. I haven't seen a lot of people do the temperature adjustment with current. It looks like with current, as temperature increases, your current also increases. But in these other voltage coefficients, it's the opposite. As temperature increases, voltage decreases. As temperature decreases, voltage increases. That's why we have this negative correlation. It goes the opposite direction. And while we're here, we also have the weight, dimensions. Dimensions will be important if you have space limitations where you want to mount your PV modules, the type of modules, some other information here, and warranty, and shows, typically you'll see a picture too of dimensions so you can see what the module looks like. Here's an example. We have a solar module that has a VOC of 44.1. We also have an inverter with a max VOC of 24 volts. If you are trying to connect this module to this inverter, you're going to put too much voltage on that inverter. So this combination is not compatible. This is why comparing the module specs with the inverter specs is important. UpTop Solar has a string sizing tool available. Not only will this help string size, but inverter selection, module selection, and temperature compensation. My name is Gwendoline SB and I own UpTop Solar, and thanks for joining me.